Welcome to Brain Vision.
Okay, so from the table of the saturated refrigerants 134a temperature, pressure is equal to 700 kilopascal, which is 0.7 megapascal. We'll find the saturation temperature is given as 26.69 degrees Celsius. So which means that the inlet temperature is about 26.69 degrees Celsius. And then at pressure equal to 160 kilopascal, the corresponding saturation temperature is negative 15.6 degrees Celsius, which means that the exit temperature in this case is negative 15.6 degrees Celsius. So therefore, the temperature drop here, which is the change in temperature here, should be equal to T2 minus T1, which is negative 15.6 degrees Celsius minus 26.69 degrees Celsius. And this will give us negative 42.29 degrees Celsius. So this is the value for the temperature drop during the process, okay? And now we can apply the energy balance equations. And we know in this case, the rate of change of the kinetic energy, potential energy, and the internal energy is 0. So we have E dot in is equal to E dot out. If we expand it, we have M dot times H in is equal to M dot times H out. As you can tell, M dot can be cancelled out. So therefore, I have H in is equal to H out, which means that the enthalpy throughout the process is constant. And then if we go back to the table at the back of the book, okay? So at a pressure 0.7 megapascal, we'll have the enthalpy is equal to 88.82 kilojoule per kilogram. And then at pressure 160 kilopascal, we'll have the enthalpy of formation, which is HF out here, is equal to 31.18 kilojoule per kilogram. And the specific enthalpy of evaporation, which is HF G here is given as 209.96 kilojoule per kilogram. So now we can determine the quality of the outlet, which is X here, which is equal to HR minus HFR over HFG, which also can be equal to H in minus HFR over HFG, since we know H in and HR is equal to each other. So if we plug in the values, eventually you have the quality of outlets is equal to 0.2745. And now we can try to determine the final specific volume of the refrigerant, okay? So the final specific volume, which is the V2 here, is equal to Vf plus X times Vfg, which can be equal to Vf plus X and then times Vf minus, Vg minus Vf, okay? So the Vf here is the specific volume of a saturated liquid, and Vfg here is the volume change per unit mass during the vaporization process. And Vg is the specific volume of saturated gas, okay? So we know we have from the table is equal to 0.0007345 meter cube per kilogram. And we know the quality of the outlet here is the 0.2745. And we know Vg is equal to 0.12355 meter cube per kilogram. If we plug in back to the equation, eventually we'll have the final specific volume in this case is equal to 0.03445 meter cube per kilogram. And this is the answer for this question.